guys, welcome to Math Spellbook. I'm your host Peter, and basically we are just going to do a little bit of exploratory mixed fusion of math and physics today. Hey Slender, hey Zach, how's it going? So Zach, I'll give you a shout out. If you guys are not familiar with Zach's work, he basically does math streams as well as mainly go over infinite series, I believe, as well as give some lectures on linear algebra. So if you want to check out like his streams for infinite series or just basically any type of math in general, just check out his channel. So there we go. Yeah, there we go. Nice. So what's the best part of your guys' day so far? Actually, I should restart the timer. Just say hi to you guys. So I think what we can do. So I think we'll just shrink my one browser here. Do this because I hardly write on the top right anyway, so I think that should be okay. Shifted apartment today, so very stressed. Oh yeah, like you mean you move into a new apartment? Is that what you mean, Slender? Okay, so my other browser has all the books we need, so I think I'm going to bring down, did I open it? So we do have our quantum chemistry book, but we're not going to get into that right away, so because I think I'm going to go into a little bit of Spivak. I don't know if I opened Spivak, so I probably have to find it. Gotta find it because I don't think I opened it. I thought I did, but I did not. This is the problem with me. It's like I have so many math and physics files that I'm like, no, I want to open this one, not that one. Where are you? There you are, Michael Spivak. The only problem with this is that it doesn't have a it doesn't have a bookmark section, so I can't even go into the chapter I want to go into. Well, we're going to the chapter 1, so yeah, we moved into a new apartment. Nice. I can send you a bookmark PDF of Spivak. Oh, you can? Oh, okay. Let me see here. Maybe I could find it on Google, actually. Or maybe like they got smart and it's like, no, we're not making your life easier. But I will disengage my model, so that way I'm not blocking any of the info. Yeah, I was reading like a little bit of Spivak, like on chapter 1 at least, because of Penn Center's like real analysis course. Actually, oops, didn't mean to do that. So actually we should put this like this, and then like this, and then we'll just zoom in a little bit so we can read everything. Oops. I'm clicking stuff by accident just to see stuff. Okay. Alright. So I think that looks fine. Now actually, like one one idea in math I thought was pretty cool was like proving that you can make numbers out of nothing. Oh, whoa, that is way too thick. Let's see, numbers. Well, actually, the whole numbers. The whole numbers are the natural numbers. Let's just do this. Yeah. From nothing. I remember reading this in, I think, like a book. Oh, you want me to check? Let's see. Oh, yeah, I see it on Discord. Just give me a second. Well, actually, first I should probably close this version of Spivak. And thank you for that, Slender. I appreciate that. Let's see. Just trying to pick which file I should save this in so it's easier for me to find it. Alright, let's open this and drag this down. Okay, there we go. Yeah, now we got some easy navigation there. Thank you, Slender. I really appreciate that. And also, I'll probably bring this one down too. I don't know if you guys are familiar with the mathematical methods of in the physical sciences by Boas. Where did I put my pen? Oh, there it is. Yeah, I always thought that this was a really cool, like, I don't know if it's a proof or anything, but I thought it was really interesting. So, like, the thing you need to know is just sets, or at least, like, what a set is, and the empty set. So the funny thing is that, like, an empty set, well, first, I guess we should define what a set is. A set is a collection of objects. I'm pretty sure a lot of people in chat know that. Like, you know, it could be any set of objects. It could be like a list of names. It could be numbers. So the set of natural numbers is gonna be like 1, 2, 3, ... You know, the ones that we can count, the ones that we're familiar with. And then basically an empty set is just basically a set with nothing in it. So yeah, and the most unique thing about it is that an empty set is not equivalent to a set containing an empty set. And from what I am told, it's easy to imagine an empty set, just a regular empty set, as just emptiness, like nothing, whilst a set containing an empty set is like a box, like with a empty box in it. So, you know, it's a good way to visualize it, I think. So the thing is that the nifty thing is that then you have to go into the definition of a cardinality. Cardinality. Hopefully I spelled that right. And then, like, cardinality is basically how many elements there are in a set. So if you had, like, let's say a set A, you had 1, 2, 3, 4. Then you would basically say the cardinality of it would be 4 elements in this set. So it's the amount of elements that are in the set. And what's fun about it is that, let's say we treat the empty set as sort of like, well, since it doesn't contain anything, we would say it's equivalent to our version of 0. And then if we had a set with an empty set in it, it has one element, so we consider that 1. Now, the fun part is that when you get to higher numbers, so how do I get to 2 from here? Well, the fun part is that you can put an empty set with a set containing the empty set. And by the rules of cardinality, or at least like the way they define it in mathematics, is that these would still be considered 2 elements, because you can actually have a set in a set, and that would be considered 1 element. So thus we have 2. But how do we get to 3 then? So for 3, we would have to do this. And I think that's pretty nifty. So it would just keep going and going, but the overall idea is that we created numbers out of nothing. Which is pretty cool. Like, it's pretty cool though. Like, I think I remember seeing this in Roger Penrose's book, The Road to Reality. And I thought it was like a cool, like, I don't know if it's a proof or anything, but it's sort of like kind of brings a little bit of life to the math, you know? It actually shows that numbers come out of, like, I guess, like, you can consider it like an ether of reality. It's like numbers, just, they be. You can make them. You can make with them, you can play with them, you can, like, mess around with them, you know, that sort of thing. So hopefully you guys, like, enjoyed that little demonstration there. And I think that's a really cool way to introduce numbers in a way. I mean, I don't know if it will be cool for elementary school students because they'll still be confused. But, like, I'm pretty sure, like, if you showed that to, like, maybe, like, a curious high school student, maybe they would find that very interesting. Because I think that's what everyone wants. It's like they want to make things out of thin air, but they just don't know how to make things appear without making it too overly complicated. And of course, like, you know, it uses a little bit of imagination too, which I think is really, really cool. So let's go down here. Because I think, like, the first chapter, yeah, it goes through the properties, so... Hey, Mean Machine Rex. What's the best part of your day so far? So today we're just gonna have a little fun. We're just basically gonna do a lot of note-taking, but at the same time, we're just gonna, like, basically, like, read and research. I guess this is my version of research, even though it's probably, like, not much. It's like research into, like, understanding what my understanding of math and physics is. So the basic property of numbers. I had some yummy cake. Me, just basically stream, and, like, one of my friends is actually from, came from, like, he used to live in my state, but then he basically moved to another state, and now he's, like, in my state, like, currently, so, I can't wait to meet him tonight. So, like, that's something that's about to come, but I guess so far, it's just basically being able to do stream with you guys today. So, yeah. Usually, like, when I, like, read up on math and stuff, I usually just, like, read. And, like, I try to let myself be inspired from what I've read. But at the same time, like, I don't do problems that much, so... basically doing problems is, like, usually something that I have to do more of. I mean, do any of you guys have any, like, special plans, like, today? After you guys are done with, whatever obligations you have to do today? So I think they're gonna go over the properties. Yeah, because they have to have a 0. So, property 1. why it's so thick, actually. Yeah, I'm starting not to like this program. Well, I know it's a browser program, but I just don't like how like it continuously makes it like very thick. So I think I'll go back to the basics here. Oops. Didn't mean to expand it that tall. Yeah, we'll use this side. I can only make 3 of these, so there we go. Yeah, I like this one better actually, because this one is like no, go away. And it's easy for me to move. I don't have to click like I'm moving. Oh, that's 5%. Wow, why is it so distant here? We'll drag this around. Oh, reading The Hobbit? Nice, nice. Yeah, like, okay, so we got the basic, so let's do, because like I'm gonna rewrite what I wrote in the last one, so from natural numbers to, oh, from nothing, yeah. From nothing. Because basically we're just given the definition of sets. So sets are a collection of elements, which could be practically anything. And we have the empty set, which is basically just a set that doesn't contain anything. And the empty set is not equal to a set containing the empty set. So we also have to remember cardinality. The amount of elements in a set. That's like a nice way to actually bring about things. And then basically, so how do we make numbers from these empty sets? Well, we start with an empty set which has a cardinality of 0. And we have a set that contains the empty set, which considers as cardinality of 1. And then we can move on to having a set that contains an empty set and has a set that contains an empty set, which is equal to 2. And then we just keep going with this process. And yeah, that's basically the basic idea. I don't know if you guys have ever seen this before. Like, when I first saw this in a book, I thought it was like really cool. Of course, I'm rephrasing because I'm on a new writing program, but I just basically went through it very fast. So that way we can just get back to what we were doing before. So now we're on the basic properties of numbers. Okay, so we'll just underline that. The empty set is a compact. What is that supposed to mean? Mean Machine Rex? I mean, that's the first I've I read of that. Oh, what do you mean? Educate me. So I think this is first property. If A, B, and C are any squares and a plus so that's the first property. I'm pretty sure we're all familiar with that. Yeah, it blows my mind too. I have yet to understand it fully. Oh, I learned it in real analysis. Oh, okay. I see. Yeah, I still, like, I think this Spivak's calculus, helps you learn, like, real analysis, like, techniques. I think, I don't know. So property 2. So I think this first chapter is just basically taking us to the rules of math. I mean, like, in a very rigorous, formal, proof-wise view of it. So this basically gives us the number 0. Because technically 0 was invented. I'm pretty glad they actually made 0. Let me just drag this over here. And then we'll drag it up here. And property 3. Oops, didn't mean to write that B there. Such that, so basically giving us like an inverse of a number. First 0, then I. Yeah, because like I think like when you actually, what's fun about it is that when you break stuff down, like in math, you begin to realize that, oh, the reason why there's so many branches of math is because, I mean, like with the numbers in general, like when you think about it, it's like, why do we have like we have the natural numbers, and then we have, well, first we start out with sets, and then we have elements, and then we have the natural numbers, and then we go from the natural numbers to the integers, and then from the integers to the rational numbers, and then we go to the irrational numbers, which is technically the real number, and then we go to the real numbers, and then we go to the complex numbers. And it's just funny because like all those different sets of numbers, they're all meant to make sure that the rules of arithmetic remain intact, like they don't fall apart. And I think that's really cool. And I think that's what kind of drives people into, like, I guess the complexities of math, or at least learning the game of how it works. Which is pretty intriguing when you think about it, because it feels like it's in a world of its own. But of course, math is not a spectator sport, so, you know, you can't really, like, you can't really say you know math after just reading a math book. You actually have to do the problems in it. You know a lot for a non-math major. Well, it's because like I just developed my curiosity around math, and then I just saw its beauty. So, you know, like this discovery I made was basically just from me reading books. And like when I started learning on like, why do we have complex numbers? Why do we have real numbers? Well, obviously we know why we have real numbers now, because there's always an infinite amount of numbers in between each number. Each whole number, I should say, each natural number. But you know, like, we have to make sure that we get to those numbers in between, right? Because we have like decimal places and stuff, and that also helps us with measurements. But when I learned about why complex numbers exist, I was like, oh, that's why. Because when you actually look at every number set, it seems as if like it has its own set of additional elements, but it still maintains the foundations of arithmetic in it. So the rules of arithmetic still apply to those numbers anyway. So, and like when complex numbers are invented to make sure that the rules of arithmetic were maintained in, like, I guess math in general as a whole system, you begin to realize like, oh, so there's like rules here, but there are ways to like make new things out of the rules to make sure that the rules remain consistent. Which I think is why math is looked upon as like the science of pattern finding. Now, of course, we don't call math a science, but at the same time, it feels like a science. But it also feels like an art too, so it's like whatever you interpret it to be. Because I think these rules are basically like primary to what makes like higher mathematics have like, I guess like, how should I say? The rules basically kind of give you like, I guess like, it's like playing the game of Go, I think. It's like the rules are easy to learn in Go, but when you play it, it's hard to master it because there's so many places you can put stones at. But just because you can put the stone anywhere doesn't mean that every spot is going to be a good spot to play in, if that makes sense. But that doesn't mean you can start with a very random spot and like work your way up to actually making that spot work for your game. No. I don't think the comparison. I don't think like. I mean, the thing of it is that like I am flattered, but I don't think I would like equate myself to like Ramanujan. He's a master on his own right. He's in the category all on his own. What's surprising is that like well, I guess it's because he didn't have a formal education. Is my... Oh yeah, it's a little bit off. Let me just shrink this a little bit. Wait, did I go down too far? I think I went down too far. Oh, don't do that, please. Guess I'm gonna have to use my mouse to deal with the book. Yeah, I went too far. Luckily, thanks to Slender, I have a bookmark I can access. Basic properties. Okay, let's just scroll down to where we were. Yeah, he reads books, I think, mostly from Britain. Yeah, he didn't even know, like, basic proof techniques. So, like, you know, I guess I'm just learning math the way he learned it. Just basically reading books and trying to understand, like, the technicalities. But at the same time, like, it doesn't mean that I'm good at arithmetic or like, using algebra to my advantage. So we've written down the sixth property. Here we go. This is where we were. Yeah, in 1 is not equal to 0. Let's just pull this up here. I know I saw a list in this chapter and I could just write the whole list down, but I feel as if I have to like look over each one just to like see what details that are in there, just so I don't miss anything. Maybe his brain was very good at pattern recognition. Is that supposed to be demystifying? Or de-demizing? Oh, systemizing. Okay. Gotcha. Yeah. I think that's how, like, mathematicians build things. Like build mathematical ideas. It's just that they have to build, like, I guess, like a system that allows them to interpret a certain pattern. I'm pretty sure with prime numbers, like, they're trying to find, like, what's like the pattern here with prime numbers. There must be a pattern or some sort, or maybe there isn't. Who knows? Because it seems random. Like, I was actually watching the ABC, no, not ABC, the Apple TV show, was it, it's not Prime Objective. What was the name of that show? Now it's gonna bother me. I know it's Prime something. Prime Target, yeah, that's the show. Yeah, I've been watching that show actually. It's pretty good. I mean, like, it's like cool that they're actually making a show about a mathematician, which is like pretty rare. Numbers that equal. So I'm guessing they're just showing us like the commutative and the associative and the distributive properties. Oh yeah, that's right. You did recommend it, that series. Yeah, it's a pretty good show. I love it. I love that show. Pretty intense though. So we have property 8. One detail. Let's see. Property 7 is important consequences. If it does not necessarily. If an A is not 0, and so is equal to 0. So property 7, what does property 7 say again? Every number A is not, that's not equal to 0, there's a number just right. Property 7 has 2 consequences. If A times B is equal to A times C, it does not necessarily follow that B is equal to C. For if A is equal to 0, then both A and B, A times B and A times C are 0, no matter what B and C are. However, if A is not equal to 0, then B is equal to C. This deduction, yeah, I mean that's pretty much given. Maybe it's not obvious, like when you explain it to a child, but like, let's see. Also, the consequence is that A times B is either A or B is 0. All right, so we have property 9. Oh, oops. Property 9. Which states that if A, B, and C are any number, any numbers, then this is, oh, this is the distributive property. Yeah, so this is like the distributive property. Yeah, to comprehend higher maths, the brain has to develop the stage where it can handle abstract thinking. Yeah, that's true. I mean, everything in math is abstract when you think about it. Which I think is the reason why a lot of people become so confused. So this is the distributive property, so... Actually, let's take a look at our properties over. So this one is basic. So the number one is more of the I think they explain it further in the book, because like I don't want to get the terms confused, because I think it's commutative, associative, and distributive. I think I lost my place. Oh, here we go. Let's see, for example, the usefulness of property 9. We will determine that. Okay, so A minus equals B. A minus B equals B plus B minus A. So hence A is equal to B. The second justification times 0. We already know this immediately. So yeah, associative. Yeah. Because I think like 0, like if you add 0, I don't know if that's considered an identity, but I think the identity one is when you multiply by 1. Usually the big, like usually like the terms involved in math I sometimes forget. So associative is like when you add stuff together and they still equal the same on both sides. The same with multiplication. And like commutative, I think, is like when you do something like a plus b plus a. 0 is additive identity. 1 is multiply. ID. Okay. That makes much more sense. It follows immediately by adding. I'm probably getting bogged down in the details. Oh, thank you for the follow. Is it curious? Curious. Curious Raditus? Or is it Circus? No, it's not Circus. Surus. Or is it Curious? Like, thank you for the follow, Curious. I appreciate it. Hopefully I'm pronouncing your name correctly. And if you're in the chat, what's your best part of your day so far? What's the best part of your day so far? Yeah, every time when you guys drop a follow, it always makes me so happy, because I'm like, wow, we got a lot of people that love math on Twitch. Just the cloud name. Lost all the creativity. Oh, okay. Yeah, because the way I read it, it looks like it's reading curious. Because I think of like C-I-R as like sir, but with the C, and then Rus. But I think, but I don't know if I'm pronouncing it correctly. If I'm not pronouncing it correctly, it's fine. I mean, just, if I'm not pronouncing it correctly, it's not fine. That's what I mean. Hey, Famish. I skipped, school IG. Like, what do you mean by that? Oh, are you talking about, like, the best part of your day so far? Are you, like, a college student or something? Work on some math, I see? Yeah. Basically, we're just, like, taking notes. So, like, before, So, like, basically, we're just trying to learn the basics of numbers, like, the rules. So we went over, like, how to create numbers from nothing. So, like, basically, like, you have an empty set, and then basically you have, like, a set that is not equal to a set containing the empty set. Then we went over cardinality. And then basically I kind of just showed a little bit of what I've learned from a book, like basically making an empty set equate to basically the natural numbers. So basically I just showed that you can make the natural numbers out of nothing. Of course I didn't show this, like I've seen this in a book, but like I thought I would share that with you guys. And now we're just doing the properties of numbers. We're just writing down the properties just to basically get ourselves up to speed. I'm just practicing writing letters through Microsoft Word. Oh, okay. What's the letters of what are the letters for? Are you writing for a letter are you writing a cover letter for a job, or like something for like school or something? Okay, so there's 9 properties. So we have the associative law, we have the existence of the additive identity, okay, the existence of the additive inverse. Oh, they are just random stuff. It's one of my online classes. Oh, okay. But it's good practice. Ah, I see. That's good. Oh, there's more properties here. So we have the distributive law. So let's see, the trichotomy law. For every number a, one and only one, of the following hold. Okay, a is equal to 0. A is in the collection P. I'm guessing P is just any set. Okay, so this is basically telling you an element can take on the identity of either one of these, but it has to be only one of these. I mean, I don't mean just an element, but probably like a number. I think that's what they mean. So it's like one number. Okay. I think that's a property that a lot of people would probably miss. Because, like, I guess we just do arithmetic more often that we don't talk about what makes a number. Or, like, what we classify as what forms a number takes, you know? Because when we think about it, like, 0 is the only number that seems like it's, like, on the borderline between, like, negative and positive. And most people would probably not know that 0 is an even number. Which is really interesting because, like, you know, people don't think about it, you know? It's like, if you divide 0 by 2, what do you get? You get 0. And, like, that's still divisible by 2, which is, hence makes it an even number. which means that 0 is not an odd number, which is pretty funny. But yet you can still divide but yet you could still divide like an odd number by 0 and it still comes out as 0. But then again, like, would 0 be considered like an odd or even? Now that's a really good question, actually. That's a really good question, because you can still divide 0 like over an odd number and it would still give you 0. So I don't know if they call that a neutral number or something like that, because it's interesting, actually. I don't know where I actually heard that 0 is an even number from. Huh. Now I'm trying to rethink of everything, but you know, like, I don't know everything, so, you know, and I probably don't want to know everything, because if you know everything, you know, there's not much to learn, and like, where's the excitement in life in that, right? But that's actually a really good property. I wasn't familiar with the trichotomy Kotomi law. I don't think I can ever say that word. Let's see, closure under addition. Oh, okay, now we're getting into closure, which I never covered in like math, actually. Like, I'm pondering on things with you. Yeah, right? And I think that's the fun of it. That's why, like, with this channel, it's not all about just basically me just like telling you guys the math knowledge I know or anything. It's just basically me just coming up with these thoughts on like what makes math, or like what is it that I'm not thinking about within math that I've taken for granted, or what is it about physics that I've taken for granted that I didn't think about deeply enough. I guess, like, you can say my streams are sort of like diary entries, or or my notes, online notes, or something like that. Whichever you prefer. Where was it? Oh yeah, an addition is in P. Okay, so closure under addition. If A and B are in P, then okay. I'm familiar with that. I usually see that in definitions of vector spaces. I think with vector spaces, that's when I started to get familiar with, like, oh, these are like the same rules, like, within, like, I guess math in general. Because I never, like, I don't remember doing problems with vector spaces that much. I just remember the definition, but I never really dealt with problems that basically say verify that this is a vector space. Let's see what we got. If 0 is divided by I and it equals 0, what does that say? Yeah, because like it seems like 0 is like a bordering point for all numbers, so maybe it has a category of its own. By number, does the book mean 1 in an infinite set? I think like when it says number, it's talking about because I think we're just talking about the properties of numbers right now, so I think it means like the natural numbers in this case, or the integers, I'm guessing. That's what I think it's defining a number in this case. Hopefully that makes it clear. Curious. Actually curious, I'm wondering, like, how did you find my channel? Were you just looking on Twitch and trying to find math streamers? Or did you find me in a different Discord server? Because we're almost to 50 followers, guys, so I'm pretty stoked. I'm pretty stoked. Of course, like, just because I get 50 followers doesn't mean I can be affiliate yet. I have to have, like, I think, like, well, at least, like, I think, like, at least 1 or 2 people watching. But that's fine. That's fine. I still will do this channel even though I'm not affiliate on this channel. I mean, I'm affiliate on my other Twitch channel, but at the same time, it's like... I don't want to put that on you guys because I'm the one that has to make the content. Oh, it's break time. Since it's break time, I remember... I feel like I want to watch something, but it has to remain math related. Let's see. I was actually watching this, Mathematical Maturity. Just have to turn my browser stuff on. Do you guys know why they call them rings and fields? New Twitch account, straight to math category. Ah, I see. Well, I'm glad you found our channel. Curious. And if you want to join our Discord server, and you just love math and physics, you can join our Discord server as well. Do we know you already? Let's see. Well, I think like rings and fields. So I think fields, they follow us, like they do have the properties of mathematics, like what I've listed in my notes right here. But I do believe that they take some rules out of that. So I think there was a definition of a field in I have another web browser open with linear algebra done right by who wrote this? Sheldon Axler. I think he defines a field. Let me see if I can find it. Somewhere here. Definition of list and length. Where is it? Addition. I just want to know what a field is. I know he defines it somewhere in here. A field is bigger than a ring, I think. Yeah, because like is it complex numbers? No. Like it's giving F as a field, but I just want to know what its prime definition is. That's all I'm looking for. Because I know there's some rules. There's some rules within a field. Discretion. Let's see. A field is a set a field is a set containing at least two distinct elements called 1 and 0, 0 and 1, along with operations of addition and multiplication, specified all properties in 1.3 list. So it has to be commutative, associative, identity. So it's basically like the same rules for like what you see in a vector space, but I think it only revolves around numbers, not vectors. But it contains 1 and 0, so I guess that's why it's called a field. Division. I wonder if the names have meaning. Yeah, I forgot what a ring was. Like, actually, like, let's look that up. Math, rings. Let's see. A ring refers to a set of elements with two operations, typically called addition and multiplication, that specify certain specific properties, especially acting like generalizations of the integers where you can add and subtract and multiply, but not necessarily divide every element by another. The key feature is that multiplication is distributive over addition, meaning you can expand products like regular algebra. I mean, that's what it says on like the Google oh, actually I should turn my model back on. Actually, like, how many minutes we have? Like, we have like 10 more minutes of break time. I'm gonna watch a little bit of this math maturity video, because I remember Slender sent this to me.
Seen him around these weeks, or been talking to him. So Tom is a longtime member of the steering committee.
So I'll just expand here, and I think I'll move chat for you guys so it's not in the way.
Program 3 years ago, 4 years ago, something like that. Longtime professor at Williams College, works in number theory, and
just move you guys over here.
Additions to the PCMI family, and I'm really pleased to introduce Tom Garrity, who will speak on mathematical maturity.
I wonder if they have subtitles, so...
Thank you.
No, it's just auto. Okay.
Most of us learned at the feet of our parents the following truth. Functions.
They just seem to have random names and arbitrary properties, yeah.
The world. Everything is described by functions. The sound of my voice on your eardrum, function. The light that's kind of hitting your eyeballs right now, function. The entries you put in your random matrices, function. It's all function. Different classes in mathematics, different areas in mathematics study different kinds of function. High school math studies second degree one-variable polynomials. Calculus studies smooth one-variable functions. And it goes on and on. Functions describe the world. I start most of my courses that way.
I mean, that will wake up a math class.
Why? For the classes, it's because I really believe it. And of course, the purpose of academia is a search for truth. And I believe that's true. Even though, if you push me,
reminds me of to not to give up.
In fact, I don't know how to define any of those words.
Haskell? What is that?
Believe it.
Functions.
And it conveys to students.
Is that a certain book or a certain author?
Is really important. Not just important to get a job, but if you want to get a good job, you should know how the world works. But it's at a fundamental level.
A programming language. Oh, okay.
I also say because it's kind of funny. But why did I do
Actually
it
curious,
here?
I'm like wondering, like, are you a student, or you like, do you have a full-time job like within STEM, or you're just a math hobbyist?
Is a true believer. Two reasons. One, it's kind of entering into the notion of mathematical maturity, a word that many college and university professors use, but not all, and which I've learned in the last couple of weeks is not commonly used by educators in K through 12.
High school student?
And we're
okay.
talking about the nature of mathematical maturity. And you can interpret mathematical maturity almost as how sophisticated you think about functions, though that's not how we're going to be doing it.
I mean, what parts of math do you love? Since you like are watching my stream, actually.
I am uncharacteristically.
Do you just love math because like you just love math, or do you love math because like it kind of relates to something else that you really like?
I don't really think about it that much.
Like computers or like science.
But because most talks that I give, it's the mathematics that's driving it. You know, if it's a research talk, I might be a little nervous that someone stands up if it's about my own research and says that's trivial, but it's a different kind of nervousness. I'm going to be talking today about mathematics, about the teaching of mathematics, and that makes me uncomfortable. So just to let you know, I am definitely more nervous than normal. I don't know about the rest of you. I did not go into mathematics
Honestly,
to teach.
I'm trying to know as much as I can. Still have.
I was wanting to learn how to do research in mathematics. Now, to be clear, I was not a naive 22-year-old. I understood full well that the day job of a mathematician in the United States
so you're just not sure, like
teaching.
You just basically just want to learn as much math as you can. Oh, okay, I get that.
I would try to bring the best of my abilities to it. I would try. I recognize.
Yeah, I got into math because I'm really into like physics.
My care and attention. I just had no interest in doing that.
Like, I wanted to learn, like, the abstract math so I can get into higher levels of physics, but I also want to learn, like, I guess basic math to learn, like, the basics of physics.
It's also the case, and I didn't have to teach for quite a while, probably into my mid-20s, when they eventually dragged me into a room to teach. It was also by my mid-20s I certainly had the belief that I certainly have very strongly now, is that I kind of bought the pop psychologist who think that all of us think we're better than we are. You know, the studies that we all think we're better drivers than we all. We all think we're better at this than we really are. So since my mid-20s, probably early 20s, unless I have strong evidence to the contrary, I believe I am average. It's sort of what average.
Yeah, I mostly like physics because it puts math into, like, physical phenomena, especially when it comes to the behavior of mass and energy.
I hope, as I say, a spouse, that I'm wonderfully,
or I should say matter and energy,
providing a framework of support for our entire lives. It's conceivable, unfortunately.
It's just funny because, like, the higher up you go into physics, and if you get into the theoretical physics route, you basically will learn more harder math.
I hope not.
Which is why I'm probably studying, like, a little bit of proof-based math too, because it's like those skills will actually help you in, like, I guess, like, in theoretical physics.
I would be average. I saw many of my fellow graduate students teach quite a bit, while I did not. They all thought they were great teachers. I thought they were all average. You know, some were pretty good, some not. And I think average is fine. I mean, it's not bad. So it was one of the great surprises of my life when I eventually had to teach. I was going to take it seriously. There were human beings in that room. But I was shocked at how enjoyable it was. Of how, and which is one difficulty in this room, is by trying to look in people's eyes to see who was understanding, who was not understanding. You know, trying to figure out how to touch that person way in the back that I can't see right now, but I'm just pretending. I mean, it was exhilarating. I mean, it's just, when I teach, it's all I'm thinking about. The number of times the crap of life, there's high school students, I apologize. The number of times when bad things happen in personal life intrude on my teaching, I think it's like 4 or 5 times in 35 years. And even then, I think I covered it. Teaching is exhilarating. And I learned a tremendous amount about human beings. Before I started teaching, I walked into that first class and I made a quick guess of who I thought was going to do well and who was going to do poorly. Of course, I thought the people who were like me in school were going to do well. So the people who were sitting in the back row, looking bored and disaffected, they were the really talented ones. They were going to do well. The people who were sitting in the front row, the people who I thought of as shameless toadies, of course they're not really creative, though they might get good grades, but they just suck up. And I was deeply surprised at how it was all over the map. I can't tell at all by looking at people how well they're doing on tests, how well they write.
Yeah.
And it opened up an entire perspective on humanity for me. But still,
can't judge a book by its cover, or in this case, the placement of where they sit in the classroom.
I identify myself as a mathematician. So it was somewhat surprising to my department back in 2004, 2005, when I was put in charge of the Williams College Project for Effective Teaching. I was suddenly the teaching guy at a school that prides itself on good teaching. And what I had to do was help mentor all new faculty in all disciplines. People in my department thought that was hilarious. Yeah, they said, "Tom, you just can't walk in and make a bunch of jokes. Not everyone does that." But I found it was great. Because I mean, imagine, Williams College is a serious school. You know, it's people care about the teaching, they care about their research. You know, I was talking to a bunch of people probably roughly in their late 20s, maybe early 30s. They were young, they were ambitious, they were full of ideas. I mean, I learned all kinds of things. It was really exciting. I don't think I helped them that much, but they really helped me learn about all kinds of things. But one thing I did learn is that they have absolutely no notion of mathematical maturity. I would sometimes say, well, the historical analog of mathematical maturity, don't worry, I'll talk more about what mathematical maturity is. It's
Unfortunately, we don't have time to, like, get into that. but it's like a good idea actually. I think like the best way you learn stuff is if you basically like teach it. So like if you're learning something like in class or something, I think the best way to learn it effectively is to basically teach someone that subject. So basically like the more you actually like, that's why I think like when you get into study groups, you basically can like teach each other like basically I guess like the subjects that you're basically learning. And then like I think it's what's fun is that if you have like two people that are studying together but they're taking two different classes, you begin to learn what that other person learned in their class, and then you begin to realize that, oh, like not only do they find their blind spots much easier, but they also like teach you something new, like that you probably would not have picked up on. And I think that's basically like the fun of like actually just learning stuff. Like if you have like, I guess like a biologist with like a mathematician, like, you know, like, or I mean like a math major, like, you know, basically like the biologist will learn some mathematical, like I guess problems and mathematical patterns that probably they may find in their biology class that they never thought of. Or like, you know, the mathematician, the math major will probably find some things related to biology that are within like certain branches of math. Like, you know, like maybe the patterns within biology will probably like allow him or her or them to come up with ideas within a mathematical theorem or a mathematical apparatus, as it were. Okay, so before we continue on with the next study session, so I think we already covered this. I don't know if there are any more properties of numbers. Okay, there is none. Okay, so there's only 12 properties. Okay, so before we carry on, biology used a lot in lot of statistics. Oh, okay. Yeah, see, like it's stuff like that, like, you know, I don't know, but then like when I learn it from someone else, I feel as if like, wow, like I can retain it, like, you know, because I learned it from a friend. And I think that's why like I don't know if this has been scientifically proven, but it's recommended that you study in pairs usually, because like, you know, like you can share, if you're in the same class together, you basically can discuss the problems with each other. In addition, that you can also teach each other like stuff based on like it's a good way to test yourself actually when you teach a subject that I guess you're learning to someone else, because it helps solidifies it more. All right, before we continue on, I will be right back, so just give me a minute, guys. Alright, we're back. So I will disengage my model. So I feel like we're gonna drop Spivak for now. And I think we're gonna go into the mathematical methods book, because this one is more of just, you know, like plug and chug math. So I'm gonna read a little bit of calculus of variations because I've always wanted to learn this. So usually I get intimidated by, I guess, like the learning curve, but I think now I really just want to be able to like take notes on it a little bit. I know I basically said quantum and like from numbers to quantum, but I feel as if like I want to be able to like tackle this a little bit. So, well, actually, let's see if we can do some problems here. Actually, because I did read this first chapter. I tried to read it as much in depth as I can. Because I want to take on some of the examples here. Because there was an example of a problem here. Because, let's see. Because we did learn about the photoelectric effect. Let's see. The energy is the upper and minus the lower. And then that equals to Planck's constant times the frequency. Is absorbed by emitted where the upper energy. So basically, when you do this equation, Planck's constant times the frequency, then you basically get the difference between the energy, higher energy to the lower energy to the higher, to the upper energy to the lower energy. Okay. Let's see. So this is the wavelength. The wavelength is basically h over the momentum. Let's see, E equals the momentum C. So the speed of light times the momentum. And so you would get the momentum from C because obviously the speed of the particle of a photon is 0. So basically you would have to get the energy divided by the speed of light to get the momentum. I'm pretty sure there's a formula that like tells you like the momentum of it, right? Let's see, we get PC is equal to the h bar times the frequency time, which is equal to h bar times the speed of light over the wavelength. The wavelength is equal to h bar over the momentum. So then in order to get, so multiply p and then you carry and then you divide the, so basically it's h bar divided by the wavelength to give you the momentum. Interesting. Actually, the fun thing about this book is that it's meant for chemistry students because this is quantum chemistry. But I love how they basically just introduce a lot of like quantum mechanical ideas into it like right away, but it doesn't assume that you know like, I guess like how like basically like the crux of physics. F equals ma, we already know that. Is the partial derivative of the potential energy over x. Let's see, we got, yeah, so we got that. The one thing about this book is that this book is very expensive. Like, at least when I looked it up, and I'm like, wow, this is such an expensive book. Luckily, like, one of you guys sent me a PDF of this book. It's the function times the wave function. Oh, whoops, I forgot to put the study timer on. So we have the time independent. We got the time dependent and the time. Is this the time dependent? Yeah, this is the time dependent one. So we'll just write the equations. Bring this up here like that. Then let's see, this is the time dependent. The time dependent Schrodinger equation. usually like writing equations down, but that doesn't mean I understand how they work. So, over I, the partial derivative of the wave function over t is equal to minus h bar squared mass plus the potential energy and the wave function. The way I wrote this part. Alright, I think we gotta move it a little bit more. There we go. Alright, so that's the time-dependent Schrodinger equation, and h bar. H bar is equal to, or equivalent to, oops, no, not h bar, just h, Planck's constant over 2 pi. Okay. Now we'll write the time-independent one. I think according to the book, they only use the time-independent one. They don't use the time-dependent one. So I should just underline that, underline this. I'll just drag this over here so we can get plenty of space. Okay, so we got the time dependent. Here we go. So the time independent is h bar squared minus h bar squared 2 times the mass the second derivative of the wave function plus the potential energy times the wave function is equivalent to the energy times the wave function. Oh, that's a constant, okay. I thought E was going to stand for energy. As for cases where the potential energy is the function of x, only there exists the function form. Which is equal to E over I, negative I E times h bar divided by h bar. Alright, these wave functions correspond to the state of constant energy. its conjugate. Yeah, I think I remember this when I was taking an online course on quantum mechanics. Like, they didn't go into like the heavy math or anything. They just went more into like the ideas and concepts. They kind of like gave you like the differential like equation solutions you needed. It was like a good way of getting my feet wet with quantum mechanics. Yeah, I do. I just don't know who I can like have as a reliable mod. Because I know a lot of people are like from other places around the world, and I don't want to like impede on their time. Oops. Oh yeah, because I clicked on my other screen. That's why it's not moving. Oh yeah, we are still writing this. Oops. Made a lightning bolt there. Didn't mean to do that. Wow, my E was like really bad with that one. For H bar. That. It's the wave function. Then e to 0. Okay, so this is supposed to introduce the stationary states. We got the probabilities. Okay, so particle 1. A one particle, one dimensional system that has phi equals a negative a half, e times e to the negative absolute value of x over a at time equals 0, where a is equal to 1 nanometer at 0 at time 0. The particle's position is measured. Find the probability that the measured value lies between x is equal to 1.5 nanometers and x is equal to, oh okay, so it's going to like the very, very tiny. Find the probability that the measured value is between x is equal to 0 and x is equal to 2 nanometers. Verify that phi is normalized. It bothered Einstein a great deal that everything came down to probability and not the intrinsic nature of the particle. Yeah, I think like there's a lot of stories about that, like with Einstein, like kind of getting bothered by the fact that, oh, there's only a probability that I will know the future. Usually in the laws of physics, we're so used to like being able to predict the future just as equivalently as being able to predict the past. Excuse me, guys. So it basically says find the probability that the measured value lies between. So let's see how they did it. Let's see, a tiny interval change. Goes from, yeah, that's X. Let's see the desired, yes. Which is equal to, right. Okay. Then we use equation. Okay. Let's see, use for. That's not what I wanted to do. Oh. I just don't want to see the answer because there's like okay, I guess I'm gonna have to do that. So let's see, for a system whose function at time and position, so this is equal to 32. I wonder where they get these numbers when they do measurements. It's like they basically are getting like random functions by just the wave function. But I'm like wondering, where does all this math come from? It seems like they just basically like put the particle through some like machine and basically say, okay, give me a wave function where you're gonna be at. Where A is equal to nanometers. Find the probability of, okay, so X dot dot dot. Luckily I have my calculator with me. 2 X is equal to okay, so we need to find the probability, and I think the probability is like you have to so I think you have to do this, and you have to do it by its negative conjugate, so because I'm trying not to look at the example in front of me, just so that I can better remember it if I don't remember it. Yeah, if I get stuck, I'll just basically have to look at it and then I will bear the consequences. So I think the x in this case is supposed to be the difference between the two. I'll take a peek and see. Oh, so that's the. Oh, so basically it's like multiplying the small little tiny difference. Okay, so all the x's in this case. Excuse me. So they use 1.5 nanometers. A is 1 nanometer. So in this case it's 1.2. I'm trying to see why they maybe that's like the initial point. That's why they started there. So nanometers times e to the negative 1 nanometer. Just drag this over here. I think we'll just move it like that so you guys can see it. Then we'll do it like 2 nanometers squared. And then we have to multiply this whole thing by the difference, which is 0.0021 nanometers. Luckily I have my calculator with me, so we'll just type these numbers in, shall we? Oh no, it's like 1/4. So we're dealing with like very teeny tiny numbers. So 1. Oops. Didn't mean to hit the clear button. Luckily I didn't write the whole thing. Don't you just hate it when you basically put in like every single thing you need and then suddenly like, whoops, you deleted it by accident. 1/4. Then multiply that by 1.2 times e negative 100 times then we multiply that by 100 1. So it comes out to be 5.8 times 10 to the 5. Then we have to, so the probability Let's see. So they just wanted us to find the probability between 1. Let's see. I don't think. Let's see if we did it correctly. No, I don't think we did it correctly. Yeah, because they have 2 points. So what did I do wrong here? For the system whose state function at time position at time of position measurements is find the probability that the particle is found between let's see. I think I forgot something. Yeah, I think I forgot something in the equation. Let me just see if that is what I'm thinking of is wrong. What I did wrong here. I keep coming up with like 5.8 to 10 to the 5th power. But here they say the answer is 0.0000256 at 258. What numbers am I not putting right here? Let's see. It says desire 1.15. Okay, so that's 5.15. What am I missing here? Let's see. Treat the interval as an insubliminal. Wait, 5 points. Okay, so yeah, we did that. Did we use the wrong? Were we supposed to use the? Maybe we were supposed to use this approach. Yeah, maybe we're supposed to use that approach instead. Is to restrict ourselves to the solution. So it says in subliminal, so maybe we have to do this formula. So let's just bring this up here. So maybe we have to do probability from 2.22, well, 2.2000. That's what I meant. And then do it from this end like this. Meaning that we have to do so we gotta do it like this. It's always trial and error, right, guys? Always trial and error. The original function they gave us was 32 3 over pi to the 4 multiplied. Yeah, this is going to be fun because we have a lot of x's in here, which means we might have to do integration by parts. In here, so we're left with, if you guys hear any noise, that's like my my printer. I think like my parents are printing something out. Okay, yeah, I think we're gonna have to do integration by parts. No, I don't think we have to. Yeah, I don't think we have to actually. Because then we can do this, and then we can do 2 times a dx, which means dx is equal to du negative like this. Yeah, and then jeez. Okay. Like that, and then we have e to the u over, so that these cross out. And then we have maybe I forgot to put the decimal point. Maybe that might be it too, actually. Which is my bad. My bad. To the square minus, no, not minus in the then minus then multiply this by still gets the same answer. So even when I did it with using the integral, it's the same answer. Wonder why that is. Am I even? It seems like I'm doing everything right. Unless that's unless they wrote the wrong answer in there. I mean, I did 2 different methods. Peculiar. Oh well. I mean, at least it let me practice like both methods on how to do it. So I think that's a bit of a win. Alright. Well, I mean, at least it let me practice with a little bit of Schrodinger's equation, at least. We got like complex numbers, units, and that lets us get into this. Okay. Alright, so I did want to do a little bit of variational calculus of variations. So I want to see what they have here. Let's make it a little bit bigger so I can see it a little bit better. Because I know with calculus of variations, it has to be like when, like it basically proves to you that the shortest distance between 2 points is a straight line. One thing about this book is that it's kind of wordy, and I don't want to like be wasting time looking through text that much. But I think that's how it is with like studying like hardcore material. At least they with the calculus of variations, I'm surprised they actually introduced a geodesic so like early. No, I'm so used to like geodesics like being introduced and stuff like with general relativity and stuff. But then again, geodesics kind of exist like things that are not involving space-time. What quantity makes it stationary where so? Another problem is this given the line so. Let's see, find the equation. So we're given I is equal to where that is a derivative of x to y. Brachistochrome. Yeah, I remember I remember hearing that from the Big Bang Theory. It's like, first, are you familiar with the Christochrome problem? And how does it vary with the calculus of variations? It's an inverted cycloid. Let's see, find the shape of a wire joining the 2 points so that a bead will slide down under gravity from one point to the other without friction in the shortest time. Here we must minimize if ds is an element of the arc length, then the velocity of the particle. Okay. Let's see, we shall later use the laws of conservation of energy. We can find V. Let's see, soap film problem. Suppose a soap film is suspended between 2 circular wire hoops, as shown in figure 1.1. What is the shape of the surface? It is clear from symmetry that it is the surface of revolution neglecting gravity, and it is known that the soap film will adjust itself so that the surface area is a minimum. The surface area can be written as an integral, and again our problem will minimize. Let's see, Euler's equations. What I've noticed is that all the math after differential equations, they seem to give a big description of like how these problems are like laid out, like what is the problem, but they basically give you a lot of parameters to deal with within the problem. Maybe that's why partial differential equations and calculus of variations is like so I guess complicated to follow, because they give you like so many parameters to deal with while you're doing the problem. Not that that's a bad thing. It's just that it kind of makes it like following it much harder, because it's like they give you like a problem, but then they give you parameters on top of that to actually make it more sense to the problem. That's just basically my explanation of why I think it's what I'm observing. It might be this is the reason why it's kind of difficult. Let's see, the speed of light in a medium index refraction n is v. This is the speed of light in a refraction. Then the time of transits from A to B. By Fermat's principle above, T is stationary. If the path consists of 2 straight line segments with n constant over each segment, then and the problem can be done by ordinary calculus, thus solving the problem. Let's see. Derive the optical law of refraction. Hint: let light go from the point A to point B via the arbitrary point P on a mirror along the x-axis. Set dt over dx, where d is the distance. APB, and show that then theta is equal to phi. Derive Snell's law of refraction. So you definitely need like you definitely need differential equations for this part. Yeah, I guess it's because like past differential equations, you're supposed to derive equations from situations, and it becomes a little bit more wordy. Let's see what we got here. Solve if g is 0 and ds is also 0 times 0. Obtain because this part I think is differential equations. Yeah, it's ordinary differential equations. Yeah, I'm not like writing much because I'm like trying to read up on like exactly what is it that we need to go through. This one I think is, it looks like I think it's second order. I mean, at least we got a quantum mechanic problem like done. I mean, it wasn't the right answer, but I get a feeling that like since I got the same answer for both approaches, either I'm doing the problem wrong or either the answer in the book is wrong. But, you know, I'm more likely to believe that I did something wrong. Oh, I guess we're done. Well, let me just turn on my model back on. Well, I didn't write that much for this section, but like, I mean, we did do a quantum mechanic problem, so I think that's an achievement. But yeah, thank you guys for joining me today on based on Math Spellbook. If you guys like if you guys like math and physics, do you mind giving me a follow if you're new to the channel? And if you're lurking, thank you for lurking. If you want to keep up with like my mathematical / physics content, please drop me a follow. I really appreciate it. In addition, if you basically were able to tune in for basically the last portions of the stream but were late in the beginning, I will be uploading this VOD onto my YouTube channel. So you will be able to catch all my VODs on my YouTube channel. And if you would like to join our Discord server to talk about your interest in math or physics or both, join our Discord server. And let's see if we can raid someone. We can probably give someone a raid. So let's see. Let's see if there are anyone in the math community like streaming. So let's see, anyone? Let's type in math then. Let's see if anyone's streaming like the category for math. There's me and there's someone else. Math fan Brian. Are they still streaming? Let's see. I can't tell if they're streaming or they're just basically testing their software. Let's try science. Like maybe we can like drop in on anyone that's doing science and technology today. Looks like there's plenty. Let's see who we can. Oh, this one. This one's yeah, I think we won't do a raid today because I don't see. I'd rather like giving a raid to someone that's actually doing like more closer to the content we're doing, and it looks like everyone's like doing more like building stuff. So I guess we'll just end the stream here. So thank you guys for joining me. Like I said, you can join our Discord. You can also give me a subscribe on YouTube, and as well as give a follow to this channel. So I will see you guys tomorrow. So take care, guys. Bye-bye.